Okay, good day, everyone. So, today we will have our discussion. Uh, we'll start with pipe flow analysis. This is actually sort of a continuation and application of what we have discussed on our previous videos, on our previous meetings. So, last meeting we discussed about the equations or governing equations in fluid flow analysis. So those equations or those concepts, we'll try to apply and relate that one to uh, pipe flow applications. Okay, so we will start with pipe flow analysis. Okay, never mind that one. This is actually slides from actually this slide is uh, taken from other subject, other course. Then I just improved this one. I just added some examples and emphasizes on the things that we need to discuss in this course, hydraulics. So actually, it's an introduction. I think we have discussed that one already. The importance of studying fluid flow in a conduits. So um, it is based on our discussion. It is already evident the practical importance and significance of pipe flow analysis in civil engineering application. So these are the flow of our discussion. Um, discuss about laminar and turbulent. I think we have discussed this one already based on our previous discussion. We have discussed about laminar and turbulent flow in properties of fluids. Okay, so about that one, velocity profile was being discussed also. We'll just emphasize, discuss that one and emphasize on some important things. Okay, define friction factor, recognize the source of minor and major losses. Actually, I divide this topic into two videos. The first video is about the pipe flow analysis, and the second video is about the application in series and parallel pipes. Okay, so as discussed on our previous topics, there are certain factors that can affect the flow or can affect the velocity and the pressure of the flow. So we have the internal and external um, constraints. You have the other constraints such as geometry, property of fluids. One. So um, flow in a flow as we know, flow in pipes um, has pressure, or it doesn't follow the atmospheric pressure because pipe is closed conduit, so it's not often open to atmosphere. So it does, or it is more than or equal or less than the atmospheric pressure. For that, we don't know. We need to compute that one. Unlike the flow in open channels, that at the surface, we can always assume or presume that it is equal to atmospheric pressure because it's a surface. It's an open water flow, and we know that for atmospheric pressure, if it is exposed to atmospheric pressure, the gauge pressure is equal to 0. So this is the typical uh, diagram of a pipe. So most pipe in our discussion are circular. I don't know if there are pipes that are applied in hydraulics or that are used to convey fluid that are, I don't know if that are square or rectangle. I've seen pipes like elliptical or a parabolic, and it's very uncommon. Those pipes were designed for a particular purpose. So for general purpose, we can presume that almost all pipes used for practical applications in water flow or pipe system are all circular in cross section. So in hydraulic applications, every values are often converted into units of energy per unit weight of fluid. So as we discussed that one already, the different types of energies were converted into what we call head or energy head. So we have the pressure head for this one, pressure head, the elevation head, and velocity head. So we express this length equivalence, the energy of the system is expressed in terms of a head. Yeah, as we discussed that one already. So we can say that the total energy present in a flowing fluid, in a moving fluid at a particular point, that energy is a summation of this head or the summation of pressure head, elevation head, and velocity head. So ako dyan na siyang gibalik-balik. Although I have mentioned that one in my previous videos and in our previous lectures, ako dyan na siyang gibalik-balik because it is very important to emphasize that concept. Okay? So applying the concept of Bernoulli's energy equation in a pipe flow, so we will consider particular length of the pipe, 0.1, say 0.1 at this point here. Then water is flowing from, presumably from 0.1 to 0.2. Then this is 0.2. Okay, so as we all know, as we discussed or as we have learned in our physics, we know that energy can neither be created or destroyed. It can only transform from one form to another. So in this case, since energy cannot be destroyed or created, so we can just equate the total energy at 0.1 to 0.2. So we can say that total energy or E1, total energy at 0.1 is equal to total energy at 0.2. So if we will sum up all the energies involved or energies present at 0.1, so we will always start or we will start at a certain datum, a certain reference. Actually, we can mm, put our reference anywhere, but for simplicity and the purpose of this discussion, we can just assume or assume that our datum is somewhere here. Then yeah. Then it is practical to assume that our datum or our reference is relatively horizontal, meaning it has the same elevations for practical reasons. So it has the same, given that our datum is the same elevation. So we will refer our energy computation from our datum, a certain horizontal line. So we will start at 0 here. So going up, diba? Musaka ta, mo increase ang atong potential energy. So going up, so plus Z1. So that's Z1. Okay, that's Z1. Then from here, Z1 is actually the elevation of the centroid of the pipe. So this is basically the energy due to elevation. That's plus. Then since we know that the fluid moving in a pipe has a certain pressure, certain positive gauge pressure. So there is a potential energy due to pressure, this one. So ato na siyang i-plus. Plus elevation plus pressure. So going upward, pasaka, that's plus. And then we have, since this fluid is moving, so we have kinetic energy, which is in form of V squared over 2G, or we shall say kinetic head. That's the energy, uh, kinetic energy per unit weight of the liquid. Okay. And then, since this datum was presumably horizontal, so we will project a certain line parallel to our datum, which is also horizontal. Although in your screen it's not horizontal, but pag paste ra siguro na kuan. So this is presumably horizontal. This is parallel to our datum, and then at a certain point, point 2 here, going downward, then we know that um, from point 1 to point 2, na certain length, di ba? Na certain length sa atong pipe. And the pipe is same, it's a homogeneous pipe, same material, same diameter. So we know that um, there's a certain friction that is occurring between the fluid itself and the fluid and the wall of our pipe, or inner walls atong pipe, because there's a relative velocity between the flowing liquid and the wall of our pipe. So it creates a resistance. It actually has a tangential stress. No, no, not um, shear stress. So nana siya there's actually a nana siya shear stress. There is actually a shear stress between the inner lining of our pipe and the flowing liquid, or yung na to nga water. So nana siya shear stress actually. So if there's a stress, there is um, there's a resistance of movement. So there must be a head loss. So far in our discussion, we haven't considered yet the head loss of the flow, di ba? In our examples, we just assume that uh, pressure is neglected. In this topic, we will no longer neglect the uh, friction. In fact, we're going to calculate the head loss due to friction. We don't calculate the friction itself or the friction force, but we will calculate what's important in this context is that we need to know the head loss so that we can design the pipe in such a way that the pressure requirement is being met. So from this point, point 2, there's a line projected above our datum. So going down, so this is actually um, head loss. The total energy actually involved is just the same with point 1, elevation head, the pressure head, the velocity head. But this time in point 2, na siya additional nga head loss. So for point 2, elevation head, from datum, that's elevation head, then pasaka, then pressure head, velocity head, and then the head loss. Okay, so if you will sum up this one, so it's Z2 plus, or elevation head at point 2 plus pressure head plus velocity head plus head loss. Okay, for point 1, di rin man ta nag-start, so wala pa nato gi-consider ang head loss. Okay, because we just consider the head loss from point 1 to point 2. Okay, so a line plotted of total head versus distance through a system is called the total energy line. So kini daw nga line, kini siya nga line, katong akong gi-mention nga a certain line projected above the datum. This one, this is the total energy grade line, TEL. So the sum of the elevation head and pressure head yields the hydraulic grade line. So, this is actually the hydraulic grade line. So this is the akong balikon ha, the total energy head total energy head is this one, the kini actually not this line. This is the total energy head. It's actually total energy head is actually the line projected if we will connect the total energy minus the head loss. Actually, this is not the total energy line kini siya nga line because gideduct naman niya ang head loss. So this is actually the total energy. Actually is the sum if you'll project if you will sum up the elevation, pressure, and the velocity, it will yield to the total energy line or the energy grade line. So this is the energy grade line. Okay. Kini siya, kining slanting. Kining nasa ubos, if we will remove this one, the energy due to velocity, if you will just consider the potential energy, the pressure, and elevation head, it is called the hydraulic grade line. Ano siya ang hydraulic grade line, this one. Okay. Balik ko nakawala ni labot ang mabaw because this is accounted for the head loss. This is the total energy line. Okay, so in a uniform pipeline, the total stress, so as I've said, there's a shear stress occurring between the flowing or moving fluid and the wall of the pipe. So the total stress is presumably constant because the pipe is homogeneous, same material, same diameter all throughout. It's constant along the pipe, resulting in a uniform degradation of the total energy or head along the pipeline. Okay. So the total head loss along a specified length of pipeline is referred to as a head loss due to friction. This one. Above the total energy line at point 2, this is the head loss. And we'll just denote it as H sub F, so head loss of the flow. So if we will equate the total energy including the head loss from point 1 to point 2, or we will compare the total energy between point 1 and point 2. So we have the elevation head at point 1 plus the pressure head at point 1, then plus the velocity head at point 1. So as we discussed earlier, this alpha, this is the velocity correction factor. In most cases, this is just equal to 1. Actually, if in the problem, if alpha is not specified, this is just equal to 1. Okay, so elevation, pressure, and velocity. Whereas in point 2, we still have elevation, pressure, velocity at point 2. So if the pipe actually is or has the same diameter, so equal na siya actually ang V1 and V2, because if they have the same diameter and no leakage between point 1 and point 2, so we can just say that Q at point 1 is equal to Q at point 2. So if they have the same area, so V1 and V2 are just the same. Anyway, this is the general equation. So aside from Z, elevation, pressure, and velocity, we have head loss added at point 2. If we will actually transfer this head loss on the left, so it will become negative. So PZ velocity minus H or head loss. Okay? So klaro na siya. That's the actually this is just the application of Bernoulli's equation on our previous discussion. Then we just inserted, I just emphasized the inclusion of head loss in the Bernoulli equation. Okay? So we have types of flow. So as I mentioned earlier on our previous discussion, it is important to know the type of flow because we will use or different equations or different approach is being used on different types of flow. So for example, if we have there are 2 types of flow, or actually 3 na siya tunga-tunga transition, but generally that's 2 na siya, the laminar and the turbulent. Then if it's a laminar flow, different approach because different governing factors, and also if for turbulent flow, we also have different approach because different naman ang governing factors of flow. So if you have different approach, we will use different equation. Although same concept, but mulahi naman gud siya ang governing factor kung kusog na ang flow, kung turbulent. So mulahi na sa dangiyang equation. Mulahi na iyang formula nga gamiton. So as we all know, the type of flow is defined by a certain measurement or a certain number. That's what we call the Reynolds number. That is the determining factor kung unsa na siya nga type of flow. So Reynolds number is mathematically defined as the density times the velocity times diameter over the dynamic viscosity. So the density and the dynamic viscosity is dependent on the type of the fluid. So lahi-lahi nga fluid, lahi-lahi nga temperature, di ba? We know that the density of fluid will change if its temperature changes, di ba? So these two, density and dynamic viscosity is dependent on the type of fluid. Kung gas, lahi na siya. Kung oil, lahi na siya. So lahi-lahi siya value. Velocity is of course velocity. It's not dependent on the type of fluid. So kung kusog, kusog. Kung hinay, hinay. Okay. And also the diameter. Diameter is dependent on, of course, the external, what we call the external constraints. So this is the mathematical equation of Reynolds number. Then in most cases, kinematic viscosity is given or mo'y known. So we know that kinematic viscosity is equal to dynamic viscosity over rho. So there are some equations nga we will use the kinematic viscosity. But actually, this is kinematic viscosity is just equal to dynamic viscosity over density. Okay? So this is the Reynolds number. So if the Reynolds number in a pipe flow ni siya, if it's less than 2,000, so we consider it as a laminar flow. Siguro na ako akong tingog kay kusog ang uwan. So if it is more than 2,000, but roughly wala lang siya ka more than 4,000, so it is nasa tunga-tunga. It's a transition between laminar and turbulent. So if it is above 4,000, so this is now the what we call the turbulent flow. Okay, so laminar flow. So laminar flow is being dominated by the viscous shear. So man siya, viscous shear dominate in this type of flow, and the fluid appears to be moving in discrete layers. So mind that if we can experiment. I don't know if we can improvise an experiment in your home or asa mo dapit. Anyway, we will just talk about the experiments later. Unahon lang nato ang theory. Later on, mag-discuss na ko how to conduct experiments even without a laboratory. Later na on the later part of this course. So, actually, for a laminar flow, makita na to na namatay gitawag og Reynolds flow apparatus na siya transparent pipe. Then we can adjust the velocity of the flow in such a way that we can see that the path of the moving liquid in a pipe is straight. So kung straight na siya, it means nga the flow path of the liquid doesn't crisscross with each other. Dili siya mo cross along the cross section of our pipe. So straight lang siya all throughout the length of the pipe. So mana siya ang usa sa mga visual indicator of laminar flow. So the fluid appears to be moving in discrete layers. So lahi-lahi na siya og layer along the cross section of our pipe na siya murag different layers, but for that particular layer the flow of the liquid will not cross to different layer. Kung asa siya nga layer, mo flow ra na siya on its straight path. So again, this is dominated by viscous shear of the flow. The shear stress is governed by Newton's law of viscosity. So the shear stress is described mathematically as the dynamic viscosity du times du over dy. So ingon siya nga in general, the shear stress is almost impossible. Yeah, it's not that equation is just approximation actually. It's almost impossible to measure, but for laminar flow, it is possible to calculate the theoretical value. So again, that the theoretical value is just an approximation. Anyway, it's approximation, but mingon mo nga, wa din ni klaro kay approximation. Yeah, pero it's based on theoretical concept, and so far for experiments mo kuan naman sad mo fit raman siya compared with other equations, but literally we cannot really measure the shear stress, unlike the axial stress, shear stress, and bearing stress of solids. We can measure that one. Nalang tayo universal testing machine, compression machine, so we can test for liquid. We cannot literally measure, but we can estimate that one using equations. Okay, so pressure loss along pressure loss during laminar flow in a pipe. So yeah, up to this point, we only consider ideal fluid where there is no losses or friction to any of other factors. So in reality, because fluids are viscous, energy is lost by flowing fluids due to friction, so it must be taken into account. Yeah, aside from the friction between the moving fluid and the pipe or sa iyang kilid, in case open channel between sa bed of the channel and the moving fluid, napod na siya actually kana siya nga friction, it's internal friction, it's between the fluid and other object. Aside from that, napod tay gitawag og internal pressure, I mean internal friction, sorry. Internal friction, it's the friction, it's the energy loss due to the interaction of fluid molecules. Yeah, they're interacting with each other. So, na siya, nana siya head loss. That's why for long pipes or tagas kay nga pipes, like a few hundred or yeah, hundreds of kilometers or thousands of kilometers, natay gitawag og mga pump booster in between. Pump booster is para mo boost ang pressure, mali mag-introduce ta og external energy to keep the fluid moving. Okay? Or to keep the water flowing if our fluid is water. The effect of friction shows itself as a pressure or head loss. So in a pipe with a real flowing or with a real fluid flowing, the shear stress at the wall will retard the flow. So muna siya makaingon nga namuhinay ang flow. The shear stress will vary with velocity of the flow and hence with the Reynolds number. So magdepende na sa Reynolds number. So many experiments had been done with various measuring the pressure loss at various Reynolds number. So by the way, this is the typical velocity distribution in flow. So if imagine this is the profile of your channel, if it's open channel, so this is the bed of the channel, then this is the surface of your channel. So ang mabaw theoretically mao na ang pinaka kusog nga flow kay wala man siya resistance. So if this is the cross section of the pipe, so this is circular, so cross section of the pipe for laminar flow, so mao ni ang iyang cross section. I mean mao ni ang iyang velocity profile. It follows the parabolic path. Then this is the shear stress. So linear ang iyang shear stress for laminar flow. So maximum ang shear stress. Makita na to nga maximum ang shear stress at the side. Then minimum at the center. So this is this is mura ni siya og gikat na to ang pipe at the middle. So sa actual mo form ni siya og mura og conical shape. So minimum at the middle, maximum at the side. So you can see that the stress at the side is maximum, the velocity is minimum. When the stress is minimum, the velocity is maximum. So minimum ang velocity, maximum ang stress. Minimum ang stress, maximum ang velocity. Okay? So in laminar flow, the path of individual particles of fluid do not cross. So as I've said ganina, mo-follow na siya by a certain flow path. So if this is man siya, let's say inner flow path, outer flow path, so mura siya lingin-lingin, mura concentric circle. Dili siya mo crisscross with each layer. So this is a cylinder with actually this is the pipe, then with a length L and radius R. Okay, so the fluid is in equilibrium, shearing force equal to the pressure force. So shearing force equal force. So actually iyan naman yung gi-equate, yang gi-derive ang shear stress. So taking the direction of measurement R, so R measured from the center of the pipe, then mao ni ang shear stress sa pipe in a laminar flow. So actually gi-discuss na niya, i-derive ang shear stress. So if you read the pages of our reference book that I gave you, if you read those pages, you can also see this derivation in mas comprehensive ang derivation. But don't get intimidated if na siya yung mga integral or differential equations, na siya yung mga integral sign. Mao na siya, that's how we measured or how we discuss these concepts. If you can observe in our books, on some other books, naadyo na siya yung mga integral, but as much as possible as much as possible, I really exert an effort as much as possible nga akong i-simplify as much as possible ang atong discussion nga dili ta mag-involve og calculus. Anyway, if you want to study in advance, or if you really want to learn the in-depth concepts and theories, you can read the book and you can read other books. Actually, if you'll just read the book that if you'll just read our reference and the pages that I give you, you will learn a lot based on the context and the derivations presented on that book. So you will learn more aside from our discussion. Actually, our discussion is just the simplification of what the book is saying. So kining atong discussion is just really simplified, pinaka as much as ako ang makaya, pinaka simplified na ni nga version, or pinaka simplified na ni nga marag level sa discussion. Okay, so yeah, nana siya equation. So gikuan ra niya ang change in pressure. Change in pressure, actually importante maguna ang change in pressure, because mao maguna ang in other especially in an open channel or nasa uban in the pipes, ang change in pressure and the length is mao maguna siya ang slope of the hydraulic gradient. So akong gi-mention ganina ba, di ba? Hydraulic energy line. So the slope of the hydraulic gradient is equal to change in pressure over length. So mabalik na later on sa atong discussion in other contexts. Okay? So the discharge may be found using the Hagen I don't know, marag French or Belgian man gani siya. So Poisal man siya gani. Basahon natin ni sa Bisaya, or if we'll read this in English or in our language, it's Puisel. But I think this is different person, si Hagen, and also this is different person, si Poisal. So that equation was attributed to them. So the Q, or the discharge, may be taken as the change in pressure over length. So if you can see this expression, delta P over L, so this is actually the hydraulic, this is the hydraulic slope, or slope of the hydraulic grade line, pi d over 4 over 1 to 8 times the dynamic viscosity. So if we will rearrange the equation, since the discharge was expressed in terms of pressure gradient, pressure gradient is alpha p, delta p over L. So if we need to know, or if we need to solve the pressure gradient or the pressure drop, so delta P is equal to 8 times dynamic viscosity times the length of the pipe times the Q over pi r to the fourth. R is the radius of the pipe. Okay? So this is for laminar flow. So laminar flow about what atong discuss. So if we will discuss the turbulent flow, as I've said, laminar flow mo lahi na sad ang iyang governing factor. It has a different governing factor because the flow is turbulent. And yeah, for the ang difference good for turbulent flow na naman gani siya si eddy viscosity. Kung karon pa mo nakadungog ani ni Eddie, you can Google this one unsa ni si Eddie. Dili ni person ha, dili ni si Eddie, dili ni si Edward, or eddy is the term, it's the phenomena present in turbulent flow. So eddy viscosity, which is not a fluid property, and kung appear naman guna siya kung naanay or when the flow is turbulent, mo na siya, it's dependent on the turbulence condition of the flow. Wala na si eddy for laminar, then mo-appear na siya if the flow is turbulent. So nanay mga laing factors, so mo na nga change na sad ang equations. So the velocity at any point in the cross section will be proportional to the 1/7 power of the discharge from the wall. So actually kanang 1/7 power gi-develop na ni Prandtl. So mana sila kana si Prandtl, sila si Hagen. Those people were mana sila ang front runner, I think, for 6-7 decades already. So mana sila ang sila actually ang nag revolutionize sa concept sa fluid dynamics or computational fluid dynamics. So but before that, those concepts, pressure, other concepts, it was already known and understood for more than a century, but mulahi naman good when it comes to turbulent flow, when it comes to moving fluid, it will open different different environment or different field or different scope or subfield of the topic of fluid mechanics and hydraulics. So the figure below shows the velocity profile for turbulent flow in a pipe. So ganina, di ba, the velocity profile is like parabolic. It follows a parabolic line, parabolic path. But for turbulent flow, the said profile is said or is estimated to be logarithmic. So mulahi na sad, as I've said, mulahi na sad ang iyang approach. Same concept, we're still using the same concept, but lahi na iyang approach, lahi na ang iyang equations. Okay, so turbulent flow is the most commonly occurring flow in engineering practice, in which fluid particles move erratically, causing instantaneous fluctuations in the velocity components. So these fluctuations cause additional shear stress. So not just the flow itself, the fluctuations because of those erratic movements of the fluid particles. In this type of flow, both viscous and turbulent shear stresses exist. So the shear stress and turbulent flow is a combination of laminar and turbulent stress. So Nagya pa ni siya, yeah, dynamic viscosity, then it's eddy viscosity. This is due to the presence of turbulent condition in a flow. Balik man. Yan, ibalik. For smooth pipe, mo ni siya ang equation nga gina-follow. So, as I've said, it is stated that the velocity profile is follows a logarithmic pattern, logarithmic line. So, the equation is nana siya log logarithmic. So, u are the velocity at a distance y from pipe wall. U asterisk is the shear velocity, which is equal to the square root of shear stress over density. Okay, y y is the distance from the pipe wall. Then k is the surface roughness. Surface roughness, it depends on the type of material sa imong pipe. So there are smooth pipe, there are rough pipe, so depende na siya. And V is the kinematic viscosity. So ganina, di ba, it's dynamic viscosity for laminar, but for turbulent, more on kung ano siya, kinematic viscosity na ang usual nga ma-involve. Okay, so we have an example. So we have a glycerin. Glycerin is a type of fluid which has a density of 1,258 kilograms per cubic meter. It has a dynamic viscosity of 9.6 times 10 to the negative 1 Newton squared per meter second. So that's the unit of dynamic viscosity. It flows with a velocity of 3.6 meters per second in a 150 mm diameter pipe. You have to determine whether the flow is laminar or turbulent. So just apply the example or the equation of Reynolds number. So density times velocity. Velocity, that's the average velocity times the diameter over the dynamic viscosity. So the Reynolds number is 708. So by the way, Reynolds number is unitless. You can check the equations nganong na unitless siya, i-match ang iyang units. Reynolds number is unitless. So it's 708, which is less than 2000. So the flow is laminar. Okay. So friction losses due to, or energy losses due to friction. So as we discussed earlier, based on the Bernoulli's energy equation, we sum up all the energy, and it is presented that energy is being lost due to the presence of friction within the length of the pipe. So when a liquid flows through a pipeline, shear stress is developed between the liquid and the pipe wall. So the shear stress is a result of friction, and its magnitude is dependent upon the properties of fluids, yeah, the velocity, speed, velocity, the roughness of the pipe. Actually, it depends on the pipe material, and of course, the length and diameter of the pipe. So, theoretically, the longer the length, the greater its energy loss, or the greater the friction. The lesser the diameter, the greater the energy loss, or the greater the friction. So magkataas, magkadako ang energy loss, magkagamay ang diameter, magkadako ang iyang head loss. Okay? So friction loss, also known as a major loss, is a primary cause of energy loss in the pipeline. So we have what we call the major and minor loss. So for major loss, wala siya ang friction because major loss because if you'll compare it with other losses, magana siya ang bulk sa energy loss all throughout a certain system. So mao na siya ang main cause of energy loss ang friction. There are other causes of energy loss in a pipe system na we call it as a minor loss. Mao na siya ang like mga faucets, mga gates, mga we have the sudden or na siya natay mga joints, muli ko ang atong flow. So muli ko ang atong flow. So di ba as we discussed earlier, if mo change of direction ang imong flow, we have what we call the change in momentum. So naatay loss of energy due to that change in direction. We also have the sudden enlargement, kalit og dako imong pipe, or kalit og or sudden contraction, kalit og gamay imong pipe. So na siya yung mga losses for that changes. Na kay mga gates, na kay mga faucets, mga any structure or any fixtures nga imong gibutang in the pipe, it can cause minor loss or one of the causes of energy loss. Okay? So, friction loss in laminar flow. So, as I've said, different jud ang discussion between laminar and turbulent because lahi na siya. Different factors ang mag-govern for the turbulent. So, in laminar flow, the fluid seems to flow as several layers. So, as I've said earlier, because of the viscosity of the fluid, the shear stress is created between layers of fluid. So, energy is lost from the fluid to overcome the frictional forces produced by the shear stress. Energy loss is usually represented by the drop of pressure in the direction of the flow. So balik ko na ko ha. Energy loss is usually represented by the drop of pressure in the direction of the flow. So magkagamay ang iyang pressure along the direction of the flow. So as you go downstream, as you go farther along the length of the pipe, magkagamay ang iyang pressure. So as I've said, the greater the length of the pipe, the greater the energy loss. So therefore, the frictional head loss can be written in terms of the pressure drop along the pipeline. So balik na siya. This is actually delta P over gamma, di ba? Rho G is equal to gamma man na siya, di ba? So head loss is actually change in pressure or change in pressure head. Diba? This is P over gamma, this is pressure head. So head loss is actually a change in pressure head drop along the length. So substituting this equation to the Poisson equation. I don't know how we pronounce it. Poisson man siguro. Poisson or Poisson. I don't know. Basta, mo ang equation. So, substituting this one to that equation. So, the head loss can be written as this one. 64 over RE. 64 over Reynolds number. Okay. Times L over D. Times the velocity head V squared over 2G. So, sayo na siya pag remember. 64 over RE times L over D times the velocity head. Okay? So, friction loss in turbulent flow. So, nasa siya, in turbulent flow, the friction loss can be calculated by considering the pressure losses along the pipe. Okay? So, in a horizontal pipe, diameter, something diameter D, carrying a steady flow, there will be a pressure drop in the length of the pipe. So equating the frictional resistance to the difference in pressure forces and manipulating resulted into the equation below. So actually, lahi siya og equation but same concept gihapon. So L over D times V squared ang nakalahi lang. In turbulent, this is gamma man siya. Lambda. No, this is lambda, sine of lambda. Lambda variant. So this is lambda. So if lambda is the friction factors, if we will compare that one to our head loss and laminar, lambda is just equal to same na sila, L over dB squared over 2. Lambda is just equal to 64 over RE, Reynolds number. So if you can observe, kung laminar flow, Reynolds number will matter. Diba? Matter si Reynolds number. But kung turbulent flow, wala na labot, wala na di na matter si Reynolds number. So, although, as I've said, same concept, but lahi na siya og equation and lahi na siya approach because this is dependent on the Reynolds number while in the turbulent flow, this is this lambda, this friction factor, actually in some books ko ani siya F ni siya ang symbol ani or FR or F or sa pa ba sa ubang libro. But regardless of the symbol, ang importante is you know that this is the friction factor. Okay? This equation is known as the Darcy-Weisbach equation. So if you're familiar with Darcy, if you're familiar sa inyong sa ba nga subject, I don't know if you have already discussed this one in your soil mechanics, in your geotechnical, Darcy's law sa paan man na siya, flowing water in soil, atong permeability, di ba? So nasa ni si Darcy. So actually same person, mao na siya nga Darcy. So this is what we call the Darcy-Weisbach equation, in which the lambda is the friction factor. Then it should be noted that lambda, in this case, or friction factor, is dimensionless. And its value is not constant. In fact, it is, in most problems, in the academe, sa eskwelahan, ihata given na siya. But sa actual, we need to estimate or we need to maybe na siya yung mga table. It actually, lambda or friction factor is dependent on, actually it's a combination of the roughness coefficient of the pipe and naman kita gitawag og Moody's equation. So it's an empirical way to determine the value of lambda, but in most cases actual practice usually na naman ko anay mga table, na naman ay there are already tables given on different types of pipe material, kung PVC or GI pipes or plastic PPR pipe. So nanana siya corresponding value for friction factor. So that in problems usually given man na siya. Na said before si Blasius, okay naman ni siya, was the first to propose an accurate empirical relation of the friction factor and turbulent flow. So as I've said, for laminar flow, so dependent si Reynolds number, but turbulent flow, di na nato makita, wala na kintahay si Reynolds number because it is already incorporated in lambda. And in fact, kini as per proposal of Blasius, lambda is a function of Reynolds number raised to 1/4 times 0.316. So in most cases, the calculation of losses and turbulent pipe flow is dependent on the use of empirical results. And the most common reference, in fact, mao gyapon nagigamit karon. Common reference is the Moody diagram. So Moody diagram is a logarithmic plot. So as I've said, the velocity profile of the laminar or turbulent, velocity profile of turbulent flow follows a logarithmic form. So ang iyang pagdetermine sa friction factor is plotted in logarithmic form. So it depends on the Reynolds number, KD. KD is actually the roughness coefficient of the pipe. And mo ni siya ang Moody diagram. Okay? So this is the Reynolds number. Actually, you can find a Moody diagram you can just download it in the internet, or you can find it in almost all books in hydraulics and fluid mechanics. So naadyo na si Moody diagram. So Reynolds number, then na si K over D. Actually, kuan man ni si K over D. It depends man ni sa kuan sa roughness sa atong pipe. So mao ni siya ang indicator kini transitional turbulence. Kini nga portion here is I think laminar. So i-plot raman ni siya sa Moody diagram. So if you have a Reynolds number, then naakay value sa K over D. So you can now plot the Moody diagram. So mao ni siya ang murag dividing factor. Muna kini diri murag laminar pa ni siya diri kay makabantay mo. Gamay ang value sa gamay smaller value ang Reynolds number on this part, diri nga part. So laminar flow ni siya kini nga region here. This region. This one here is turbulent na ni siya nga part. Okay? So we have a different roughness. On the Moody diagram, this is the ratio of roughness and the diameter. So usually, if the friction factor is not given, solbo na to ang friction factor, then we can plot or asa dapit ni si K over D, then ato rang i-plot, then ato rang i-follow. Ato rang silang iabot. Then we can determine its value sa iyang kini friction factor. Ano siyang value sa friction factor. Okay? In other books, instead of lambda, F ni siya. F. This is the value of K, roughness coefficient. So it depends, as I've said, it depends on the smoothness or the roughness of our pipe material. Okay, so minor loss. So aside from major loss, before tamo adto sa minor loss, balikan na to ha ang equation for okay, this is the equation. This is the equation of major loss or the loss due to friction in a pipe. This is called the Darcy-Weisbach equation for turbulent flow. For laminar flow, same equation but different approach. Dito na siya, RE or 64 over RE. Okay? So that is the equation for laminar and turbulent flow. For the minor loss, so as I've said, natay mga gitawag og minor loss due to pipe expansion. So from small pipe, gisumpayan og dako nga pipe. Contractions from small pipe, gisumpayan og dako nga pipe. From contraction from dako nga pipe, gisumpayan og small pipe, sini-contract ang flow. So kung mo-contract ko ng imong flow, naa kay sudden change of pressure, naa kay sudden change of momentum. So therefore, naa kay mga gitawag og friction loss. Those are just minor losses. Nakay bends, actually bends change sa imong momentum. Nakay valves, mga fixtures imong gibutang between sa imong pipes, and other fittings, unsa mga fittings imong gibutang. So these losses are usually known as the minor losses. So in case for a long pipeline, kung taas kay nga pipeline, minor losses may be negligible. Negligible siya kung you have let's say 1 kilometer or several kilometers, tens and hundreds of kilometers. So dili na kay na mo matter si minor loss kay gamay ra kay na siya. It's very small, relatively small compared to the value of our major loss, as we can see later in our example. So gamay ra kay na siya value. So for simplicity, sometimes ato na lang na siyang i-neglect. Okay? So however, in the case of short pipelines, kung short ang pipeline sa minagdaghan kay kang liko-liko, especially sa among short pipeline sa mana, we can consider that sa households, sa imong balay, di ba, in your unsa na ang subject ninyo? Engineering utilities, di ba? You designed a pipe. You design pipe in residential building, di ba? Liko-liko imong pipe. So we can incorporate that in our loss. Actually depende ra man gud agad kung ini-compute nimo gamay ra man jud kaayo, so ato na lang i-neglect. Okay? So for us short pipelines, their contribution may be significant. So the minor loss is actually dependent on the velocity head. So it depends on the certain value of K. So kini siyang K, mo ni siya ang certain coefficient. It depends ang value sa K, it depends on what type of disturbance sa imong flow. So actually it depends on the magnitude of your flow and the types of disturbance sa imong flow. So nakay lahi-lahi nga value of K. You have different value of K on different situation. So exit pipe to tank, so K is 1. Entrance tank to pipe, so 0.5. So these are just the suggested value, mga typical values sa K. Although if you'll read other books, if you read other references na anay mga mas more detailed values sa K, but these are just the coefficient. Is a multiplier man ni siya. So it should not be more than 1. It should not be equal or less than 0. So it's between 0 to 1. Okay? Pipe fittings. So sudden enlargement. So actually, same ra ni sila equation for minor loss. Ang nakalahi lang is the value of K. Ang value. It still depends on the velocity. So coefficient of expansion and the value depends on the ratio of a pipe diameter. So sudden enlargement, so dA over dB, diameter A over diameter B. So if you look at the table, diameter A over diameter B, the value is muna siya. So 0.2, 0.4, 0.6, 0.8. So it's a ratio between diameter A and diameter B. So different values of K. Okay. Money siya, sudden enlargement. Because the loss of energy is because of this region of turbulence. Nakagitawag diri og very low velocity. Kini nga part, so dako siya og dako iyang pressure. So naa kay turbulence, so naa kay energy loss due to that enlargement. Then opposite of that is the contraction. Okay, so tanawa sad ang table dB over dA. So tanawa ang asa ang A. So ang A mas dako, ang B mas gamay. Then same naghihapon siya og value equation. Different value lang sa K. In this case, A ang dako, B ang gamay for contraction. In this case, enlargement, A ang gamay, B ang dako. So ang A is the upstream, B is the downstream. So A is the upstream, B is the downstream. Okay, we'll solve an example. So water at 10 degrees Celsius is flowing at a rate of 0.03 cubic meters per second through a pipe. The pipe has a diameter of 150 mm. It has a length of 500 meters and a surface roughness is estimated to 0.06 millimeter. Find the head loss and the pressure drop throughout the length of the pipe. So find the head loss and pressure drop. Okay, so given man ang temperature, so na siya table for the density. So density is 1,000 kg per cubic meter. Dynamic viscosity is 1.3 times 10 to the negative 3 Newton square per Newton second per square meter. First, we need to determine if it's laminar or turbulent. So substitute this given to the Reynolds number equation. So first, we need to determine the velocity. So naman tay Q over A, that is equal to velocity of 1.7 meters per second. So determine the Reynolds number, density times velocity times diameter divided by the mu man ni siya. Divided by the dynamic viscosity. Okay, so dynamic viscosity is 1.3 times 10 to the negative 3. So the value of the Reynolds number is 1.96 times 10 to the, actually this is times 10 to the 5 to the 5th. 1.96 times 10 to the 5th. So it is way more than 2,000. So the flow is turbulent. So since the since the friction coefficient is not given, so we can use the aso diri. Na delivery. Okay, so since the friction coefficient is not given, so we can use the Moody diagram. Na naman tayo Reynolds number, which is equal to 1.96 times 10 to the power of 5. Then KD, so naman tayo K nga 0.06 times 10 to the 3. So actually 0.06 millimeter times 10 to the 3. Okay, kuan man na siya 0.06 millimeter man na. Okay, so the value of our KD is 4 times 10 to the negative 4. Then based on the Moody diagram, i-plot na to siya. So remember, ang atong Moody diagram is naatay K over D, then naatay Reynolds number. So we can solve for our roughness coefficient. I-plot na siya. It will correspond to friction factor, which is equal to 0.018. So based on that, we can use that friction factor to compute the head loss using the Darcy-Weisbach equation. So 0.018 times length of the pipe, okay, times velocity, which is equal to v squared man siya, 1.7 meters per second. Be careful with the unit. If meter, i-convert to meters tanan. Kung naka millimeter, i-meters tanan para ma-cancel out. So over D diameter times 2 times 9.81. So the head loss is 8.84 meter. Okay? So change of pressure. So multiply lang nato ni siya. This one is 8.84 meters man siya. So gamma times H. So gamma is density times 9.81 times the head loss, 8.84 meters. So the friction loss or change in pressure loss along the length ng 500 meters sa atong pipe is 8.86 times 10 to the positive 4. Actually, it's 86.7 kilopascal. Kung ano siya? Times 10 raised to the power of 4. Siya na-edit. Times 10 raised to the power of 4. So, it's actually 86.7 kilopascal. Okay? Okay, another example. Determine the head loss that will occur as 0.06 cubic meters per second of water flows from a 40 millimeter pipe diameter into a pipe of 100 mm diameter through a sudden expansion. So from 40 mm, isumpayan siya og 100 mm. So nikalit siya og dako. So nakay head loss due to sudden expansion. So the head loss through a sudden enlargement is given as K V squared over 2G. So first, we need to determine the velocity. Q over area, so that's the velocity, 3.58 meters per second. So, kuha na to ang ratio. 40 over, since 40 minutes siya, 40 over 100, that's 0.4. So, naman kay table, naman to, 0.4. Expansion. 0.4. Okay. So, your K is 0.7. K is 0.7. So, just multiply 0.7 to the velocity head. So, it will yield a head loss of 0.47 meters. Okay. Okay, I will just continue with this one for this video. Ato na lang tiwason. Anyway, this is just continuation. Sumpay raman ni sa tanan good. Pampa ni siya. Okay. So, energy added and extracted. So, as I've said, there is a situation when you need to add energy through your pipe system. So, kung mag-add kag energy, it will be a form of mechanical energy. Actually, pump na siya. Then, electric energy will be added to your pump or will be activated to your pump. Then, ang pump mo, tuyok siya. So, it will add a mechanical energy. Then, the mechanical energy will be converted into potential energy in form of pressure. So, rotate sa imong pump mo, add siya og additional pressure sa imong system, sa imong pipe. So, mag-add ka og energy. So, balisad, nasay uban nga, naa kay flowing water, butangan nimo og turbine, butangan nimo og palabad, butangan nimo og Tagalog, LSC, propeller, butangan nimo og propeller, butangan nimo turbine. Then that turbine will be connected to your generator. So, maka-generate ka og energy. So that energy is actually extracted from your system padung sa imong generator, padung sa imong appliances, padung sa imong nahimo siyang from kinetic energy, mahimo siyang electrical energy. Okay? So Yeah, there are many occasions when energy needs to be added to the hydraulic system to overcome elevation difference and friction losses. A pump is a common device to which mechanical energy is applied and transferred to the water as total head of the pump. Head added is called pump head, H sub P. Dili na siya HP ha, di siya horsepower, that's H sub P. N is a function of flow rate through the pump. Now, on the other hand, fluid motor or turbines are common examples of energy that extracts energy from your fluid, from your system, and that energy extracted is called the head of the turbine or H sub T. Deliver it in a form of work or form of mechanical energy, then i-convert na siya sa imong generator into electrical energy. So, going back to our go nang may malabay rin sabang dogs. Going back to our Bernoulli's energy equation, so if you will add energy, okay, if you will add energy, you should put it on the left side of the equation. That's energy. Actually, it's energy added or that's actually energy added or extracted. So that's if you'll put it in the left side of the equation, that's actually plus or minus. Plus if added, minus if extracted. Okay, then on the right hand side of your equation, that's the head loss. Let's say head loss from 1 to 2. And it's head loss is always positive if you will write it or if you will put it in the right side of your equation. Balik ko na ko ha. Head loss is always positive if you'll put it on the right side of your equation. Sa right side, always siya positive. Okay? So, power of the pump is given as rho G. Actually, it's gamma unit weight or density times G times Q times the energy added or extracted. So, ang imong pump, di ba, naman na siya power rating. So, ang power rating ko sa imong pump is equal to density times G times Q times the energy nga iyang ihatag sa imong or iyang ipuno sa imong system for the pump. Okay? So kung turbine siya, so this will become negative kay mag-extract mag-energy ang turbine. Actually same ra gihapon ang iyang power rating. So, mag-differ lang ni siya sa atong power rating. It will differ on its efficiency because wala man gyud system nga walay machine or system nga 100% efficient, so nadyo kay losses in between. So if your, let's say if your pump is 70% efficient, so ang electrical energy nga iyang i-consume is 100, ang iyang mechanical energy or pressure energy nga iyang output is just 70%. So in the efficiency, always gamay ang output, always dako ang input. Okay? Yeah, efficiency. So efficiency is power delivered to the fluid. So kini siyang power delivered to the fluid. This is actually the output. Okay. Then power supplied sa pump. That is actually the input. So power supplied sa atong pump usually in the form of electric power. So that's mo na siya ang power supplied ng kuryente. Then mo na siya ang output. So always gamay ang atong power delivered to the fluid. Always gamay ang atong input. So N is it's basically less than 1. It's always less than 1 in fact. So kung turbine sad balisad siya, since ang atong turbine, ang atong input is from the fluid man. So ang atong turbine is, di ba, motuyok siya due to the movement of our water. So mas dako ang power supplied by the fluid. Then ang power output sa atong motor mas gamay. Actually, di man ni from the kuan man ni siya. It's actually from the generator. Generator motor. Motor gyapon. Okay? So if basin taas-taas atong discussion basin nagka-kuan mo information kuan ba. Di man sa siguro overload pero basin kuan lang if taas na kaayo i-pause lang siya then i-process. Then if naamay confusion, i-recall lang ang video. I think I've discussed it man tanan so far. Ako gibalik-balik yang uban. Ibalik lang siya og play or basa mong libro or you can PM and you can send a message in MS Teams in the post nangutana mo about that portion. Okay? So mao na siya ang concept sa efficiency. Okay, I think example. So calculate the head added by the pump. Okay, so pump ang imong ibutang. So ang imong pump saksak siya sa kuryente, then tuyok ang atong pump, so it will add head. It can add power to our system. So calculate the head added by the pump when the water system shown below carries a discharge of 0.27 cubic meters per second. If the efficiency of the pump is 80%, calculate the power input required by the pump to maintain the flow. Okay? So, saan mo ni pag-solve? Power added by the pump. So, natay added by the pump. So, natay ihatag diri 0.1, it has an elevation of 200 meters. 0.2, 230. So, nakay difference in elevation of 30 meters. So, ang system gud ani is nakay tangki sa ubos, isaka nimo padung sa mabaw. So, para mosaka ang water gikan sa 200 padung sa 300, 230, magbutang ka og pump. Otherwise, kung wala kay pump, ang imong water, instead nga mosaka sa mabaw, moaga siya gikan sa mabaw padung sa ubos. Okay? So, nakay length sa imong pipe nga 1,000 meter. Nakay diameter 40 cm. You have a friction factor which is 0.015. Nakay minor loss. I don't know if this minor loss is gi-appeal ba ni pag-compute. In this case, we can just neglect the minor loss. Anyway, tanaw na to ang example. So applying the Bernoulli's equation, so point 1, tanaw na to ang point 1. At point 1, we'll just assume that this is point 1 ha. Kini siya, kining elevation, kining sani water surface. So water surface has an elevation of 200 meter. So the water surface is open to the atmosphere. So ang iyang pressure is equal to 0 gauge pressure. Same with pressure 2. Point 2. Nakalahi lang, ang iyang elevation is 230 meter. Okay, so at the tank pod, kini, we can just assume that the velocity inside the tank is 0. Siyempre kay inside the tank, dili man, your water will not move. Ang imong water will just move kung naa na siya sa pipe. Okay? Move ang imong water na sa pipe. But inside the tank, your water is basically stationary. So wala kay velocity head. Wala kay energy due to movement. Same with point 2. Okay? So, balik ta dire. So, P1, Z1, velocity head at point 1, added power, added head by the pump. Then, for 2, pressure at point 2, elevation at point 2, velocity at point 2. And then, the head loss from point 1 to point 2. So, naani siya sa right side. Plus ang iyang sign. Plus yan. Plus. Okay? So, as I've said, Pressure is equal to atmospheric pressure. So, 0 ang iyang gauge pressure. Velocity, we can just, as I explained earlier, we can just equate the velocity as equal to 0. So, the equation will just reduce to, ini, pareha ni. Although naa kay Z1 nga 200, kini, Z1, supposedly 200, but imo siyang i-minus, i-minus dito sa pikas, dire, i-minus, mahimo naman ni siyang, kuan, it will become 30. Z1 minus Z2 is just equal to 30. Okay? So, ang imong HP, the head added by the pump, is equal to 30 plus the head loss from point 1 to point 2. We already know this one, Z1 plus Z2. So, we'll just need to compute the head loss from point 1 to point 2. So, compute na lang nato ni head loss from point 1 to point 2. Okay. We will sum up all the head loss. First, head loss due to flexion. Okay? So, atong tagsa-tagsa na head loss due to flexion. It is head loss within the entire length of your pipe. Pila to yung length sa itong pipe? 1,000. Head loss from point 1 to point 2. 1,000 ang length sa pipe. Flexion is siya. Kay head loss sa entrance. Sa maning entrance, from point 1, gikan sa point 1, isulod mo ng imong tubig to the pipe. So, kay sudden sudden contraction. Kay head loss sa bend, 45 degree kuno, elbow bend. So, ni bend ni liko ang imong water. So, kay head loss. Then, from the pipe, exiting to point 2. So, you also have a head loss due to sudden enlargement. Okay? Okay. So, atong tagsa-tagsaon. So, since these three are all minor losses, okay? Minor losses man ni sila tanan. Ato lang ni siyang, di ba, ang minor loss nato is B squared over 2G. So, mausara man nato ni tanan. I think appeal sa ni siya. Head loss in terms of in terms of B squared over 2G, di ba? Lambda D over L times B squared over 2G. So, we can just factor out B squared over 2G. Ato lang gigawas. So, okay. Ato ning tagsa-tagsaon. This one is lambda, which is given as 0.015. 0.015 times length of the pipe over its diameter. So, kini nga term, these terms, kini, are head loss due to friction. Okay? Then, kini siyang 0.5. I think mao ni siya ang head loss due to entrance. So, the K of sudden contraction is 0.5. Okay? So, K to sudden change in direction or bend, which is 0.4. Then, K niya sa exit from pipe to the tank sa 0.2 is K is just equal to 1. Okay? Then times B squared over 2G. So, in that case, we already have the velocity na nanawag. Okay, I'll just continue. Head loss is 39.4 V squared over 2G. Okay, so the only unknown is velocity. So we can just solve the velocity. Velocity of the pipe, actually. That's the velocity of the pipe. So the discharge is 0.27 divided by its area through its diameter nga 40 cm. So we have a velocity of 2.15 meters per second. So with that, we can solve for the head added by the pump as 39.3 meters. Okay? So we already have 39.3 meters. Now, we need to solve for the power of the pump. The power of the pump is equal to rho times G times discharge times the head added by the pump. Kini 39.3. And ang gi-compute, ang gipangita god is what is being asked in the problem is the power input. Okay? So power input of the pump. So pila man kunay power input sabot ano niya is pilay kurente, pilay electricity input, power electric power input if the pump is operating at 80% efficiency. So this is the efficiency of the pump. This is actually the output. This is the output at the top. This is input at the bottom. So we can just rearrange the equation. That's power of the pump over the efficiency nga 0.8. So the power of the pump, this is the output. That's 1,000. That's the rho times G times the discharge times the head added by the pump. The unit of the power is actually in this case we are using a metric system. Its unit is kilowatt or watts. So unsa man ang watt, that's joule per second or newton times meter per second. That's watts or kilowatts. So that's the power divided by efficiency. Efficiency is unitless. Okay, it's 0.8. So the power is 130,117 watt, or roughly 130 kilowatt. Okay. Okay. As for this, taas naman ta. I'll just end our discussion from here, and I'll just proceed with this discussion. Ako na lang i-separate nga video para na siya di siya continuous, dili siya masyadong taas, di siya kuan para sa yun ra on your part to play and to review, dili kay taas ang video. Okay, so I will discuss in the next video the pipe flow analysis. So for now, we have discussed the flow system, types of flow, laminar flow, friction losses, the major losses actually and minor losses, and energy added and extracted in the system. Then we have some examples. So next video we will discuss about the pipe flow analysis that includes pipes in series and pipes in parallel and pipe in network. Okay, so thank you for your attention. That would be all. Okay, thank you.